Hello and welcome to this wonderful webinar with Prasad Yalamanchi. Prasad is a founder and CEO of Lead Semantics. He's been working in the field of computational linguistics, developing intelligence systems for the better part of 20 plus years. Today he's going to be presenting ontologies for automating graph LLM workflows. Who better to talk about this than someone who's developed a platform over the last 4 years to automatically work with unstructured data using ontologies? Prasad, the mic is yours.
Thank you so much, Joaquin. And thank you all those that are joining us from, I believe, from around the world. So it could be good morning, good afternoon, or good evening. And without further ado, I would like to get into this short talk related to ontologies, as Joaquin said, for automating graph and LLM workflows. In other words, this is pretty much workflows that would use AI agents, which is a buzzword pretty much in these days. The one twist is that how to make these AI agents be a lot more predictable by using ontologies, So that is what we bring to the table in this talk. I'll start sharing my screen. So we'll start by talking about the workflows themselves. Of course, we are talking about digital workflows. All workflows are like a sequence of individual tasks. I'm not going to get into the definitions of workflows and things like that, but we'll start with what these tasks are and how these tasks come together to complete a workflow. Organizationally, however, they fit into what accomplishes something for somebody is something outside of this discussion. Yeah. So a task itself is a unit of execution. So it is completely independent of other tasks. We're not getting into too much of detail there either. And it is a single design unit. It is the target of planning for efficiencies, mapping resources to doing or accomplishing this task, vis-a-vis people skills to resources, and so on. So you just we are trying to get a handle on what this task is. They're also meant to be kind of thought about as something that is reusable and something that you could repurpose it for different things, as part of other workflows even. So as we said, workflow is series of tasks that would take certain input at the beginning and produce something very useful, possibly something that will lead to an organizational goal in some cases. And probably there are other definitions for something like that. Now, the key thing here is that we are talking about automating such a workflow, which is having multiple tasks, multiple independent tasks. And something like that would have to have a master that is coordinating between these different individual tasks. You would have to move the transformation across these different tasks so that they naturally get to the end with hopefully what we are expecting as the end result. And so the handoff between these tasks become important, because the whole idea of breaking down this so-called end-to-end workflow into individual tasks, or rather putting together these tasks to make up for the workflow, is that these tasks are independently designed and you could plan for efficiencies and all that. And as such, the handoffs between these tasks become important. And that's something that we will revisit again as part of the discussion. And because of these handoffs being important, then the outputs of one task would end up becoming or morphing into inputs of another task. And so the way that second task would understand the outputs of an earlier task would mean that the data model that is expected in the second task is one way or another is aligning with the data model that is being produced out of the outputs of the earlier tasks. So those are the broad things that essentially drive the interworking of these tasks to make up for the workflow, and that in a sense will lead you to the automation. And given that that is what a task is, agents are an apt artifact for accomplishing these tasks, within a workflow. And we'll get to what agents are as we discuss here. So agents implement specific tasks. And the critical thing about agent is that, a software agent is that they are autonomous. So you don't need continuous interaction with it for it to do what it is supposed to do. So in other words, it has an internal logic driven by its own internal model. All it needs is a prodding from outside, a trigger, so to speak, and then it takes on uh, to do its own thing. And so there is a responsible execution that it is going through to produce something that it is designed for. And so that is the autonomy as we would normally expect for, how you ascribe it to live things even. And they are adaptable, given that they would have to execute on their own, show their autonomy and all that. You would expect them to be adaptable. And so by definition and by design, they're meant to be adaptable. And one of the big aspects of the design is that they interact with the outside world through asynchronous messages as opposed to synchronous messages. Your ordinary programming would routinely use synchronous messages, although more and more things are becoming asynchronous, but you can't rule out synchronous as well. So you send a response, a request to somebody outside, and you wait for the response to come back. There are certainly ample situations like that. But asynchronous messaging is what gives the independence of, you shoot it's like an email. You shoot fire and forget kind of a thing. So you shoot a message and you go on to doing your next thing. And part of it may be just to wait for the response from whoever it is that you have sent this message to. And so there is a degree of independence that gets you this. Asynchronous messaging gets you that. And a large part of how this messaging would work is also that there is a conducive environment into which these messages are sent. And one way of designing this is through message mediation using queues and things like that. We're not getting into software architecture here, but that is an idea. So an asynchronous message is shot out from an agent, and that gets probably put onto a queue. And all the attendant instrumentation is there on these queues with labels and timings and things like that. There's plenty of libraries that do that. And there is a designated subscriber to such messages, and so another agent possibly, and we'll get to that, is looking for such messages. And so it would know to pick up from the environment where those queues reside as well. And so that is the conducive environment we are talking about. And in order to accomplish this workflow, which is like series of tasks to be accomplished, one agent solving one task. Now we are already faced with multiple agents having to complete these different tasks, because you don't want to necessarily sequence these things, given that these are independent things. They could probably take on, parallelly many more requests, each agent. And so these agents are expected to interact with the environment and collaborate with other agents by sending and receiving messages to the environment and other agents. And that's how the progression through the workflow goals itself kind of moves along. And automating workflows involves these multiple agents collaborating, as we said. And so in terms of collaboration, the big part, and this is it bears repeating and stressing on, is that the message that is being sent out is understood by the receiving agent. And so in order to understand the data model that is expected of the message that is received, should be aligned with what is being sent out as part of the message that was from the previous agent. And that becomes the critical. So data model becomes the critical part as we are designing these agents. And so when we are talking about modeling, the goal of modeling is that it is to establish a shared view of the domain of interest. So there is a problem area, a domain of interest. And so there are different, actors that are interested in the same domain. And so the shared view, given that these are independent, separate actors and agents in this case, you do want the data transformation and the data that is flowing through is understood across these independent actors. And so modeling kind of accomplishes that, the act of modeling, the data that needs to flow through, the data pertaining to this domain. And ontologies are a type of ontologies are semantic models, and they are a type of modeling. And the key aspect that probably makes them valuable just out of the chute is that they are machine understandable, not necessarily machine processable or machine readable. Every other artifact is machine readable in the sense, something or the other is able to, even an XML document is read and it's displayed and things like that. But that is not what we are talking about when we say understandable. In other words, much like people, the machine itself, the algorithm itself knows to kind of really use the artifacts that are coming through the model and apply it appropriately to other models and all of that stuff. So that is machine, and hopefully we'll get a flavor of that as we discuss here further. So, and this semantic modeling, in contrast with some of the other modeling techniques that we may have been aware of over the last 10-15 years, prominent being relational modeling is one, object-oriented is the second. Relational model particularly has been prominent, given that everybody pretty much in this IT domain is familiar with relational databases. They hold these tables of data, rows and columns, and each table connected to other table through something called foreign keys. Maybe users may not know about the concept of foreign keys, but for example, if you have a customer table related to an orders table, then the order is connected to a given customer through something called a foreign key, and that becomes the critical part of the modeling technique that is engaged, so-called entity relationship modeling. It's been very prominent and it has its role to play. But then software development itself kind of led to this other type of modeling technique, which is object-oriented modeling. In its own right was very popular, is still probably parallel. These two are still parallel and popular along the way. But one is tables and keys, and the other one is objects and pointers to other objects. So it's much more related to encapsulating what is of an abstraction. So if you talk about an automobile, everything related to an automobile would be encapsulated. So you can talk about it as one single thing, and until you really need to get to the engine inside the automobile and the tires and so on, which will all be planned inside this encapsulated abstraction. And so that becomes an object, and the pointers to other things, if that were to be an object, would be a pointer. And so that is a defining technique. So objects form hierarchies, like car is inheriting from automobile and so on, like that. And so that's what an object-oriented defining characteristics. And in contrast to that, semantic modeling, which produces ontologies, are related to entities, their properties, and their relationships. Entities are pretty much what the concepts of the domain of interest, and these concepts will have their properties. Like automobile is a concept and it has its own properties and it has relationships to other concepts and so on. And so the essential thing here is that all the critical things are all that make up these entities and all that are motivated by what you see in the real world, as opposed to some systemic and data driven constraints and so on. So out in the world, what are important to your problem area, that would drive it. And they end up becoming so-called the statements as triples. So these are 3 element statements, 2 nodes and 1 edge, as in the example that's shown here, like a person connected to a company through a work for relationship. And that's also called a predicate. And so that is an ontology. Ontology is more flexible, it's machine understandable, and so it's a lot more powerful. And so why not use these ontologies as the data models for these agents? And that's how ontologies power AI agents as well. So ontologies constrain AI agents to operate within the boundaries of the task and function, that is designated for that agent. and they expose this internal ontology so that other agents can interact with it, or even and that's how the environment will also interact with it. An ontology is aligned to the central master ontology, so to speak, of the environment through alignment. And one beauty or one big power that you get with these ontologies is that they are a lot more dynamic. They allow for the so-called mismatches between the modeling elements of one model versus the other, which typically range from being semantic differences or structural differences or syntactic differences. So those are the alignments that possibly can be managed through dynamically with an ontology, and that really enhances the power of these agents, which are already independent and which is like a defining characteristic. So the more independent they are, more more powerful they become. The ontology alignment among agent ontologies is a necessary thing, otherwise they won't communicate. And this alignment, as we said, is possible in the case of ontologies dynamically, given that these semantic differences, they can be managed through, or one way or another aligned through synonym matching and hypernyms and so-called hyponyms and related to. These are different techniques within semantics. These are all the additional values that you get out of dealing with a data model as an ontology. And of course, these multiple agents, they collaborate through sending messages to each other to accomplish the goal of a workflow. In this case, we are talking about AI agents, not necessarily the old world agents. And this is where, with the LLMs that are prominent and prevalent everywhere, the rise of the AI agents is pretty much on hand. LLMs, which are the generative AI artifacts, these big language models, they take language as input and they generate language as responses. And so it's much as humans, as you see, they understand language and they produce output as language. And there are plenty of AI agents on the market right now as wrappers over plain old LLMs that are available as API calls that you can make to. Like auto GPT and the custom GPTs and so on. And in the pictorial here, these star-shaped things are the agents, and so they communicate and they are independent and they communicate with each other to accomplish a particular task, or maybe a full end-to-end workflow. We'll get to a detailed workflow here in a second. And in the case of AI agents that use LLMs, the handshaking pretty much becomes, the prompting from the outputs of another previous step in an LLM. So an LLM step probably produce an output, and you morph that output into a prompt of the next step. So that becomes a dominant technique of handshaking between these agents. And there are plenty of pros with the LLMs being the heart of these AI agents. They are naturally intelligent, so they are detecting patterns, and they know when to act. All those things. They understand one thing from the other, and they understand language, and so they increase the autonomy by that much, and they make them much more adaptable. These agents. There are significant benefits to AI agents than agents that are not inherently AI centric. And ontologies on top of it, they minimize so-called downsides of LLMs. They minimize hallucinations, and so again, it will enhance the power of each input output that is going through these AI agents. They increase the domain specificity. So ultimately, when we accomplish a business goal, they would have to be one way or another pertaining to a specific domain. Specific workflow by definition is accomplishing something that is materially progressing in terms of some business need or something. They eliminate so-called this incompleteness problem with general interactions with LLMs. And so in the net of it is that these agents are prone to producing accurate and expected outputs. So the interactions become a lot more fruitful. And so the specific example that I would want to take you through in the next few minutes, it's a workflow with ontologies and AI agents. It's in the case of ESG monitoring for compliance. So ESG, environment, social governance, is fairly prominent, and there are new rules that have just been instituted by SEC and so on to monitor if there is any compliance issues and things like that with companies that have registered with the SEC and so on. So one example here we are talking about is there are funds that are at least they come into existence by wanting to invest money in these ESG funds, so to speak. And so, and they publish certain investment guidelines as a charter for themselves. And based on the charter, they solicit investors, and then they take the money and invest in securities that fit the particular, guidelines, or, whatever the constraints that they have, imposed on themselves to fit this ESG profile that they have published. And they periodically make their filings and disclosure to regulators like SEC in the US. And so monitoring for compliance by whoever the regulator or designated officers would be to follow certain triggers. They cannot obviously go through monitor every company there is on the roster. So they would, for the sake of efficiency, would probably look for certain triggers. And very likely it is coming from some alternate data, not from the submission or a disclosure given by an individual company, because they are, a third party is a lot more reliable. So alternate data is meant to be third party, like news or social media and so on. In this case, news is a good source of these triggers. And some critical information is flagged in this news item, for example, that may be talking about a certain ESG item related to certain underlying security or a company, right, in which a fund may have invested in. And as such, that becomes a triggering point for a monitoring agency or a group or a person. And the steps that would take to inquire further or investigate is to take that security that is in the news for certain ESG related information, figure out which fund has invested in those securities, and look for their disclosures and see if there are any discrepancies between their investment guidelines to their disclosures to what is appearing in the news. That is one sample use case, and that's what is a workflow. And in this picture, I will quickly go over all the elements of this workflow. These star-shaped visually is an AI agent, as is in the legend here. And in this case, this agent is wrapping a graph rag component. Graph rag stands for Graph Retrieval Augmented Generation. RAG is a very prominent technique in terms of dealing with domain-specific documents to get LLMs to focus on these documents to produce answers. Graph is the next level, that makes much more accurate answers possible from the same underlying documents and so on. And so these pictures are all AI agents that are graph rag agents. So we have 3 of them here. And then we have a compliance master that is tasked with monitoring ESG compliance. And then the workflow would start by the master looking for a trigger, searching for certain trigger. And given that this agent is tasked with overseeing alternate data, which is like a news source, so it would look at maybe a security is identified and along with an ESG mention in the running document somewhere in the news item. It goes back, and that is sent to a securities database in-house, maybe public domain. And then from there, it is kind of goes to the fund, so-called ETFs. This fund has invested in this security, and then knowing that that information, now the trigger would be to find out for that fund what are the guidelines. And so in order to do these guidelines, these agents, these are all natural language interface, question answering kind of, they feature question answering style interfaces, much like what you expect out of ChatGPT style. And so they produce these question answers, they produce the question, and the question is reformulated by the central ontology component, which is another agent, and then sent to this agent, and that agent that is handling the guidelines will send the appropriate answer specific to maybe it is a GHG gas emissions for a company. And so that gas emissions related guideline that the fund may have put in their prospectus, for example, that is sent back. And similarly, the question is shot to a disclosure document, disclosures with the regulator, for example. So the corresponding disclosure element related to GHG gas emissions, and all are corralled back here, marshaled back to this agent here. And then if there is any threshold crossovers or flag something that needs to be flagged, that gets back to the master, and then the compliance is kind of concluded in terms of identifying whether it needs to be flagged as something to be investigated, or whatever the next set of course action may be. The key thing to notice is that these AI agents are all seeded with ontology inside. They have their own ontologies specific to whatever the type of documents that they are dealing with, for example, or the knowledge they are dealing with. And these ontologies, they all kind of get mediated through these intermediate master ontology agent, so to speak. And so the so-called synonyms, hypernyms, hypernyms, as through these question and answers that they flow back and forth, is all language. And so because language need not be one-to-one, and so because there is plenty of ambiguity, and all that is sorted out through these ontologies. And the net result is that a very independent set of agents come together to deliver a very complex workflow. With that, I will close. If there are any questions, I'm willing to take.
Yeah, there's we do have to conclude the webinar, and thank you very much for your presentation, Prasad. There is 2 questions from Alexander Garcia. So perhaps you can follow up via the comments, and I'll just put them up on the screen so we can contextualize the questions he's coming from. Is there any difference between prompting LLMs with a knowledge graph versus just simply text? And is this proven that ontologies minimize hallucination, or does it mean that I have to train my own LLM or keep using those pre-trained ones? I think the notion that needs to be dispelled is how valuable are ontologies in the context of LLMs. We really do have to drop, but maybe can you take a shot at it in 30 seconds?
30 seconds would be too soon, but I'll just try that. The critical thing is that ontologies, you can take an off-the-shelf pre-trained, like OpenGPT, GPT-4. It will still have its hallucinations. It is still not domain specific enough, not with RAG even. But with an ontology, which is an ontology by definition is domain centric. So there are, you are already putting a data model, but in the format of an ontology, right? And so in that sense, you through prompting and all that, you make sure that the GPT-4, the way it interacts, is limited to or guided by the ontology that you're doing, and it is routinely done without having to again train further these GPT-4 models. In fact, the fine-tuning itself is reduced by using ontologies, and it is very well proven. Our own product does that.
Alexander, for more questions, you can reach out to Prasad. Thank you all for attending this presentation, and I welcome you to the next one. Have a good rest of your day.